the office has grown over time, and some people look at MTO and they say, I barely recognize it. We went from a micro devices office to a microsystems office, right? And microsystems has been in the name forever, but we were really physicists doing physics work, and now we've expanded where the physicists are being paired with people who are looking at the bigger picture of what a microsystem is, and that includes a lot of the computation work. As IPTO into IXO, which kind of disbanded into lots of small bits and pieces and across the different offices. MTO's portion of that was the hardware portion of computation, and that is a growing portion of our portfolio. Obviously, is recognized by ERI. And as an RF guy, what I recognized, right, is as good of antenna design as I could do, and as good of filter design as I could do, right? The actual advancements were being paced by the digital advancements in the back, right? And so I quickly realized I needed to learn as much as I can, even though I'm more comfortable talking about waves than I am bits. It was something that I recognized you need to actually adopt those techniques. So what you're going to see today is ERI, which is about computation, but computation particularly close to where our sensors reside. So you're going to see people kind of bounce back and forth, all right, sort of between this line. So what you're going to hear is someone like YK Chen, who's going to kick us off, and he led an RF and optics group, right? But he's also going to talk about what he wants to do in terms of embedded processing and next generation processing. You're going to hear Paul Tillman, who's really leading the RF intersection of RF and machine learning. So where on that line, which side of this does it really reside? We don't know. We don't really care, right? So we had to try to make a boundary so we knew who was going to be in each session. But you're going to hear kind of a mix of sensor development and computation development. But we also then have some hardcore computer engineers and computer scientists that will be speaking with you as well. So between the physical world where wars are fought, air, land, sea, and space, you heard a lot about that in the plenary sessions and how that's changing. And then you also heard I2O's description of cyber, right, is where MTO wants to reside, which is that line where we gracefully pull information in from the physical domain, put it into the digital domain, how we sort it out, and then disseminate it back out. And so it's the intersection of the spectrum, right, and how computation is done on that information and how that then gets distributed. That is what is interesting today. So spectrum, sensors, and electronics, they're separate thrusts, but they're all obviously on top of each other. And that is going to be reflected in what you hear today, where you're going to get a mix of all of that. So I'm going to get off stage so that you can hear from the people that really matter. They're the ones that have the ideas. We're a bottoms-up organization. Right? I veto ideas. I don't create them. We want to put the task of idea generation in the community, the PMs representing the opportunity from the community, and us just putting light organization so the community can reach its full potential. We're not a top-down organization. We're definitely bottoms up. So YK Chen will start us off. YK, very lucky to have him. He's a National Academy member. He's a National Academy member in the United States. He's a National Academy member in Taiwan. He is recognized for his work in integrated optics, optical systems, millimeter wave systems. We hired YK to be a jack of all trades. We knew his background covered many, many different things that we have, and you need that in an office. So the number of times someone comes to my office, I got a new idea, who do I talk to? I'm like, you could always talk to YK. Yes. He's got a breadth that is dazzling. So YK.
Thank you. Yeah, thanks, Bill and Monica. They called me up about this time last year. So a lot of cool stuff like ERI we'll be doing at the MTO. So I retired from Bell Lab and joined more cool stuff here. So back in Bell Lab, yeah, I was working on some of the point-to-point radio and for 10 gigabit for 4G and upcoming 5G. And I was also doing the fiber optics transmission from 100 gigabit to 800 gigabit when I left with coherent technology and silicon photonics, etc. So since I joined DARPA, I tried to find something relevant for the warfighter. Then we'll say, hey, can we do, how can we use the ultra-wideband to help the communication and computation for the DoD environment. So as you can see, I've been working on some of the point-to-point radios to cover X-band all the way up to E-band, 90 gigahertz for the company. So because our base stations backhaul are scattered around the world, and each country has its own FCC, so they have multiple bands. So we developed very wideband ASIC to cover 3 major segments of the band, so we don't have to build a special radio for each country, which can be very expensive. So for the DoD environment, so can we imagine we can build a radio which can cover all the way from HF up to 250 gigahertz, right? So in that case, we can provide a spectral dominance. We can operate the frequency any narrow band from HF up to 250 gigahertz, or we can spread the signal across the whole spectrum and to provide very secure communication. That's what I'm very excited to do it. So in that case, instead of using very narrow band communication like what we are doing today, and how can we use ultra-wide frequency range to generate different waveforms to deal with different capacity requirements or the security requirements, LPD, and sensing, and then also to protect against the weather, the interference, and all those things. We will say, hey, that sounds great, the idea. But first of all, we have to build the hardware to deal with this. So in that case, we have to build a radio which get enough bandwidth for sure. But in the DoD environment, as compared to point-point radio, which is really protected, right? So you have to deal with the fading, with interference, and the vehicle move around. So in that case, we need a very good dynamic range of the RF front end and the data converters to capture all those defaded signal and recover it, right? And then how can we integrate these things inside a relatively portable or movable box and eventually put on like Dick Tracy's watch, right, in the future? That'd be wonderful, right? So you can choose any frequency you like to operate and any bandwidth you like to do. So that's something we are interested to look at. So to do that, so we really need a semiconductor technology to do it. So if we look at like all those analog RF front-end technology, you can see the blue dots is the 3-5 technology. They are pretty good frequency response up to terahertz transistor. But if you look at all the integration for the silicon to shrink to the needed to shrink to a Dick Tracy's watch size, the green dots, they are really only 300-400 gigahertz region. So one of the things we like to look into the ERI, besides the digital electronics, we also like to look at the mixed signal, mixed mode IC technology to push the integration and the speed of transistor toward the terahertz. So in that case, we can build this wonderful radio. So we also need to interface with CMOS. As Bill said, we have to process the signal. We have such wideband signal. You try to digitize it, and for 10, 12 bits resolution to give you dynamic range. That means you have to multiply the sampling curve by 10x for the digitized data. So but your original data is very relative, a few gigahertz or tens of gigahertz bandwidth. Why I need a terahertz backplane to do it? So it's important we try to condense the digitized signal through the machine learning techniques or the digital signal processing, reduce from the digitized data from the analog world down to the extract the real signal data in the gigahertz range. So in that case, we're interested in the real time machine learning techniques. A lot of the tensor processor, you can do video or voice very well, but not in a very fast environment. So we need a low latency processing. So the traditional DNN things is good for inference, but in the real-time learning, adaptive, you have to feedback, that's a long latency. So can we use some kind of feedback kind of network, like a reservoir or RNN, to do this more efficiently? That's something we are very interested. Then hopefully those things can be integrated with our front end to give you the Dick Tracy watch. So that's what I'm interested to pursue. And any input you have, we'll be very happy to have.
All right. Thank you very much. We have a couple minutes, so YK, we'll give them a snapshot into the behind-the-scenes office interaction, right? Ultra-wideband is interesting. Technologically, it's going to push the state of the art. If you're going to go 40 gigs instantaneously, you're going to have really interesting compression algorithms close to the antenna, whatnot. The challenge I think we're facing is how do you do that in such a way that it isn't just more exquisite and hard to use, right? We already turn off a substantial number of features in radios that are for things like security because the warfighter just needs to communicate when they need to communicate. So there's something really good there about translating ultra-wideband into ultra-reliable, right, and not just more secure. So really balancing the security and the reliability issue, I think, is the type of thing that we're studying to figure out how you would run a program that's not just more finicky. Right? We've got enough finicky radios out there. Right? So, all right. Andreas Olofsson, you've heard about Andreas on the plenary speech. Andreas had a small design startup, got his start on Kickstarter. I think that's a pretty rare fact for a electronics company. And so he's been leading the charge in next generation design. So Andreas.
All right, so I've been designing chip products for about 20 years, 10 years at ADI and TI before I started my own company. And I don't know if you know the quote, genius is 1% inspiration, 99% perspiration. That is never more true than in chip design, right? So 2008, spent about 6 months creating a new architecture, new instruction set, new memory architecture, network and chip. Best time of my life. So much fun. And then I spent the next 8 years slogging through, porting it, designing boards, chips at 3 different nodes, and then finally boxes, right? That's what you need to do hardware design. So, you very quickly get through the innovation, and then it's just a slog. So I came to DARPA to try to address that. Make that more efficient. Make it, maybe it's not going to be 50-50 between inspiration and perspiration, but not 1 to 10. So we've seen this graph, right? Complexity growth, and we talked about that during the ERI panel on Wednesday. And the point I want to make here again is that the cost of design, the cost of complexity is not one thing. There's no panacea. You have to address all of them, right? So the POSH and IDEA program tries to address design, verification, and layout. But to really make a big impact, as we know from Amdahl's law, you have to address all of them. So just to summarize, right, that's the end state of the POSH and IDEA program. You truly will be able to take source code and schematics, push the button, and get the blueprint, the GDS2 out for boards as well as chips. So now what, right? So we talked about silicon chip design. I feel pretty confident that we're going to have a big impact in that space. But chips alone don't mean a lot, right? It's the system that matters. So if we go from silicon to systems, taking a look at some of the very complex systems, and we have similar problems. You have an explosion in the cost and the people involved in these systems. I mean, it comes back to our brains, right? Our brains, our capacity to comprehend detail has not grown over the last 50 years, but our systems have gone exponentially more complex. So that means we need more people, each one specialized, which means we have more communication overhead. So it's really one of the same kind of complexity binds. But if we look at the F-35, for example, right, possibly the most complex machine on the planet, all kinds of modes, signal processing equipment, control systems, in terms of capabilities. If you look under the hood, right, you're talking about tens of millions of lines of code, thousands of suppliers, thousands of unique integrated circuits that need to be integrated. So the software and hardware. This is the reason why this has taken over 20 years and cost $55 billion in R&D. So how do we solve that? Pauschin idea is not going to solve the problem. Pauschin idea is just going to take care of the physical layout and some of the reuse. It's not going to take care of the software integration and the testing. So the question is, can we emulate a complete system? And the question here is really, can we create a platform where we can do enough software testing and what-if scenarios and trials without having to fly the airplane? So kind of becoming a, really emulating the real airplane as much as you possibly can. It's a big challenge. We had a workshop on this during the ERI Summit, and we had Lockheed Martin there, we had Raytheon, we had Waymo, as well as all of the EDA companies who today provide emulation systems for chip design. And the outcome was, this is a really, really hard problem. There's no obvious solution. But it's a very important one. So it's not just airplanes. If you think about enormous constellation of satellites up in LEO, you don't want to just upload the firmware and hope that it works. It's a distributed system. You need to really know before you upload them that this will not break down. Self-driving cars. You want to upload a new self-driving software, right, to the cars, to a fleet of millions of cars. You need to know that that's not going to cause everybody to turn right when they should turn left at some place. So, there's really multiple domains that need this kind of capabilities, and there's some fundamental basic technology missing, and there's also domain-specific technology that needs to be put in place. So that system emulation is one area. So that really addresses the software verification challenge. Second one that I'm interested in is space processing. So if we look at where space processing is today, it's really pre-EDA. So if you watch the panel with Bob Kahn and Lynn Conway talking about how computer science was really the way out of complexity, right? You put the knowledge into the EDA tools to make it easier to design. In radiation-hardened electronics, we're still, that knowledge is still inside people's heads. We don't have EDA tools for radiation-hardened electronics. And as a result, the radiation-hardened processors are lagging commercial processors by 1,000x. So this is going to put a severe limitation on what we can do. And I know that people are putting commercial electronics up in LEO in industry, but there are radiation environments where that's just not acceptable. So what do we do there? Do we just stick with the low-performance processors, or do we figure out a way to easily design radiation-hardened electronics? So I do think there's a path, and I think the government has a big role here. The EDA industry has always been motivated by commercial interests, the big companies like Intel, Qualcomm, and Broadcom. There really aren't a lot of commercial entities that are selling these chips in volume. So, but it is an important avenue. So, so we could invest in creating EDA tools for radiation-hardened electronics if we want to be able to auto-generate these kinds of chips. So imagine having a chip design for a commercial on-the-ground processor. It's been well tested in a certain node, and then push of a button, you get the radiation hardened by design. The soft error rate is improved. There are checks for single event latch up rules that don't exist today. I think that could be quite powerful. And then finally, I'm interested in manufacturing at the board level. So there's probably 1,000 different products on the board level for every product on chip design today, right? There's 5,000 to 10,000 chip designs done every year. Well, maybe not 1,000, but there are hundreds of thousands of new boards being manufactured every year. And within the DoD, procurement and build to order could possibly disrupt all the way we do business, right? So if you imagine having a warehouse full of components, having the fabs, the PCB bare boards, right, which are not that expensive, sitting on the shelf, all the components you can imagine, like an Amazon-style warehouse, and then roboticized manufacturing plants, meaning that you pick the assembly, the PCBs off the shelf, you pick the components off the shelf, and then you have a built system out on the other end. And for those of you who have been involved in PCB manufacturing today, that is not the way it works. There's lots of manual labor, lots of places for mistakes, and this is in big contrast to semiconductor manufacture, where there's diagnostics all through the line. Everything is run by robots, very little human handling, very little room for mistake. This is a big opportunity for US manufacturing as well as for the DoD to increase efficiency. So those are kind of my interest areas: radiation hard electronics, electronics manufacturing, and system emulation. So you know where to find me if you want to talk about it. Thanks.
All right. Great stuff. So we got a little bit of time. So I think we've been kicking around something in that large-scale emulation for a while. And we just held the workshop. And I've got a dream. And if you talk to me long enough, I will say this, because I only have a couple things I say. I just repeat them across large conferences. So I want a car that is, after 10 years after I bought it, is 10 years better, right? Not 10 years worse, right? And that means that I get an oil change, I get a better computer, I get a software upload, right? It means that I've actually got a digital twin or something that's in the background that is allowing progress to be made behind my back, so you don't have a test and eval cycle to get something new in the system. So if you can actually sell a car 10 years after for more than you bought it, right, then we'll have succeeded. And I don't really care about cars. What I do care about is the military systems that would impact. Right? So we can design quickly all day, and if we can't get into the field, then all we're going to do is just create better stuff that we complain that people aren't using. So that's why you see that shift to some of the system discussion. All right. Speaking of which, Steve Trimberger, who hosted our alternative computing session yesterday, we're very glad to have him. He's our newest program manager. Actually, I don't know who's newest, but one of our newest program managers. Very often we get dignitaries from other countries and say, how does DARPA work? What is it about DARPA that is unique? And it's people like Andreas, Steve, Serge, all of my program managers, right, who press pause an otherwise thriving career and join the government. It does not happen in other countries. Right? You're on the government side or you're on the industry side. So having people like a fellow from Xilinx come and lead an alternative computing thread or whatever you're going to tell people you're going to head is very exciting. So Steve.
I don't have any slides. So I don't
Yeah. Okay.
So
I'll take it.
I'll let you hand that. And right, so I'm going to stand up here. This is different. I'm an industry guy, so I'm going to do a lot of things different. First thing I'm going to do different is I don't have any slides. So you have to look at me, so I'll stand up here. The second thing is an industry guy says, Bill, your idea of a car that's better 10 years will not work because they want to sell you a new car. So in the technology transition phase, this might be a brilliant idea and it'll work, but when you get to technology transition, I'm afraid we're going to have some issues. So anyway, that's kind of a perspective I'm going to try to bring to DARPA. The other thing that's different about this, I don't have a program yet. So, oh yeah, good. So I don't have any particular axe to grind, although I'm going to grind a few other axes. What I'm going to do is talk a little bit about about the bounds on the problem as I see the bounds on the problem. So first, a little bit about me. I started at Xilinx just about 30 years ago, so I left about a year ago. And so saw a lot. Actually built technology that spans about 5 orders of magnitude in computational complexity. So these are things going into small embedded systems and large computational installations. So I've seen a lot of different technology, but not specifically on the application side, on the technology side. And in that time, this is the programmable logic business. This is FPGAs. Leverage Moore's law. But the FPGAs that you see today are not just Moore's law scale-up of the ones that were being built in 1984. There's a lot of other technology in there. And so that was a lot of what I was doing, doing things like 3D and optical and combining microprocessor plus FPGA. There's all that stuff that's inside there. A lot of the things that we talk about today that beyond Moore or whatever, yeah, that's been done in those devices, actually been done throughout the industry. So it's kind of interesting where, as we look at sort of the ERI premise that, well, scaling is slowing down, we need to look a few other places. As an industry, we certainly have. And those of us out who come from the industrial side say, well, what's new about this? I've been beating my head against this problem for a long time. What's different, and actually let me talk a little bit about the arc of the technology development. There's the invention side, which is a little bitty piece of it. You do this invention and you have this great idea, and then there's this risk reduction phase where you work on the invention, you make sure that it's actually it will really work. And then there's what I call adapt and adopt, where you filter. The technology does a lot more than what you need, or than what more, I should say, a lot more than the intended application. And you filter that. And then there's the press to product. And this is where, this is the huge amount of expense, and the value gets added. And then there's loss of control. And that's the measure of success, when you lose control over it. I think a lot of times we're very afraid to lose control of our marvelous little invention. And so, yeah, you've got to be able to do that. I'm going to consult my notes here so I don't forget anything of importance. I'll just forget the unimportant stuff. So, yeah, as I come into the commercial bias, that means I have tremendous respect for digital synchronous CMOS. So we can step back and say, no, I'm going to violate some of these rules. I'm going to do something very, very different. That's okay, but if you step off the moving sidewalk at the airport, you might get there sooner, you might make more progress, but the joker sitting down on his cell phone is going to pass you up when the wheels on your luggage start to wobble. So if you get off the technology moving sidewalk, and there are several, right? Obvious technology scaling. There's an EDA moving sidewalk. There's an educational moving sidewalk. So, gee, we would like the new vision of the world is we need to be doing analog design. By gosh, not only are there no analog designers, their professors didn't learn it either. So you're in trouble if you're going to step off that moving sidewalk. So the industry guy says, you do something different. Right? You have to solve that problem. What is the problem you got to solve? And that's the other issue with the industrial vision of technology development is you have to solve all the problems or you get nothing out the end of the pipe. If you have a technology, it's wonderful, but you can't test it. You can't prove the reliability? No. You have to be able to do that. You have to be able to design it. You have to be able to build it. You have to manufacture in volume reliably every day. Okay? So all this stuff, all this boring stuff, right, doesn't sound DARPA hard, but it's enabler, and if you don't do it, you don't have it. And if you can't do that, if the industry won't produce it for you, you don't have the technology just as certainly as if you hadn't developed it up front in the first place. The other aspect of this is schedule. Schedule? What you talking about schedule with research? The week you lost up front dithering about what you're going to do is the same week you lost the back end when you're trying to deliver it to your customer. Schedule is schedule, and you only have a certain amount of weeks. And so time is of the essence always in the process. We'll skip that one. Talk about it later. And I'm going to hit this topic of solving the whole problem, because it came up a little bit with Andreas. You can remember his slides. We have become good at looking at our new novel technologies and saying, yes, I must include EDA in it. So we have task one, build me a new design technology. Task two, build me the EDA for it, right? But we don't have task three of how are you going to test it. Task four, how are you going to prove the reliability. Those sorts of, we kind of leave that to somebody later. If we're going to leave that to an industrial partner or someone to prove that out, that's a big expense, and we're going to have to pay them for it. We're going to have to let, again, I'm going to talk to the industrial guy, you got to let those guys make money. So that's the other thing. Just part of the problem we will leave for those guys, and you better pay them for it. So that gets me to the how do I really see the future here? We do have to step off a moving sidewalk. We don't have to step off all of them. And when we do step off that moving sidewalk, we're going to have to be running hard. So I'm looking at running hard in devices and architectures, and I'm trying to leverage digital synchronous CMOS as much as I can.
Thanks, Steve. I think I'm going to save questions for the panel, just because I think I want to make sure we get to that and be able to answer questions from the office. Actually, that's great. All right, so now our newest member, Serge Leaf. Good news is lots of fresh opportunities to co-opt minds to create new programs. So Serge Leaf joins us as a VP at Mentor Graphics. So long history in the EDA world, but also in venture-like roles. So kind of understands that innovation and creating innovation and getting it to exist in the world side of things. So Serge.
Thank you, Bill. All right, so let's see. As Bill said, I'm the newest member of the team. So I spent my entire life in electronic design automation. I started working on simulation and synthesis in undergraduate school, and then basically joined Intel and developed simulation, place and route, silicon compilers to enable the original microcontrollers like 8051, 8096. I was on the 386 design team and so on. So I have actually personally left behind probably 10 million lines of code doing different EDA things, mainly in synthesis and simulation. And I spent 28 years at Mentor Graphics, where I was managing a large division focusing primarily on system kinds of applications. And also I was in charge of venture capital incubation mechanism at Mentor, where I looked to identify new opportunities, invest in them, develop them into businesses. Some of this through acquisitions, some through licensing, some through organic development. So as an example of a program that happened in my division, this was a program that focused on secure silicon. The idea was, can we add security subsystem to SoCs? And so we created a technology that injected the security subsystems into the chip, which contained the hardware root of trust, key stores, meters like odometers and stuff like that, and so that you can essentially defend against supply chain attacks, reverse engineering attacks. We can encrypt or obfuscate logic blocks, unlock them after production with keys and stuff like that. And so when these chips that contain the security subsystem are manufactured, during wafer test, we ask the security subsystem to basically create its birth certificate. The birth certificate is established, and from that point on, this thing becomes authenticatable, trackable, and so we can enable all kinds of things like provisioning, turning on and off hardware features and stuff like that. So that was an example of something we did. So when I started talking with Bill about joining this team, he told me, you must have a passion project, something that you've been wanting to do for a long time, and this may be a platform for it. And it didn't take me long to think about this, because there is one biggest problem in EDA that has existed for a long time, and it has to do with raising the level of abstraction. In 1978, we designed chips by drawing polygons, transistors. And the designer efficiency was, maybe we could design something that had 10 transistors, 20 transistors, and so on. Then in 1982, we went to gates. So now we could design things that had 10,000 logic elements. Then in 88, we went to RTL. And the intent was, well, this is going to take us to millions of transistors. Well, we got stuck at RTL for 30 years. Nothing happened. We're still designing at RTL level of abstraction, and yet the chips that we're building today cost $300 million and contain over 20 billion transistors. That's why we're seeing all kinds of gaps that are being formed. We can't verify what we design. We can't really integrate things that we design and so on. So the challenge that I'm interested in is nothing less than to revolutionize the way that digital chips are designed and raise the level of abstraction. Not one, but maybe two levels. Not just up to the behavior, but up to intent. This is an idea that my peer, Steve, convinced me is the right way to go. So the problem has been articulated back in the day as follows. You describe functionality and intent. You push the magic button, and then out comes your system. Right? And when I talk about system on chip, I don't mean just hardware. To me, system on chip is an SoC and accompanying software stack. And so that has been the vision. And over 30 years, the industry and the academia tried to chisel away at these problems, but at best had partial and peripheral successes. And in 2007, one of my customers actually informed me, hey, you guys have been wasting your time for 25 years on this. We solved this problem. The system synthesis problem is done. You don't need to worry about it anymore. So I started asking them, so what are you guys doing? What do you mean by that? And so they described this methodology to me, which was, hey, we describe what we want to construct in UML. Then we manually decide what is going to be hardware, what's going to be software. The stuff that's going to be software we take through automatic code generation, and stuff that's going to be hardware we take through the synthesis process. And we have created this constrained platform, which is a little PCB that has a microcontroller, FPGA, memory. And so everything that we do maps into this. And we achieved incredible economies. We can turn designs in weeks. It costs us next to nothing. And so at the time, I dismissed this. But as the time went on, I kept coming back to this and thinking, you know what, maybe there is something here. Maybe solving this problem actually is, the solution is hardware and software meet, as opposed to just thinking about it from synthesis perspective. And so the more I thought about it, the more I thought this is a problem that can be solved by combination of a soft platform and high-level synthesis. And so the idea that I'm interested in exploring is taking the notion of a platform that contains a CPU, embedded FPGA, domain-specific IPs, security mechanisms, and making the platform soft, in other words, configurable, so that a synthesizer is actually given a choice of maybe 30 CPUs. The synthesizer is given the freedom to rip up and re-implement the on-chip communication system. It is given the freedom to take parts of the behavioral model and figure out how they map into accelerators that are available in the domain-specific library. And And the notion of synthesis historically has been we're trading off performance versus size. Well, I'd like to expand that. It should be performance versus size versus power versus security, where security is yet one of the optimization dimensions. Anyway, continuing, the second problem I want to talk about that interests me is secure design. So right now, I guess up to now, defense systems were basically printed circuit boards largely, and various parts were designed at various places, and there was some kind of methodology, or is some kind of methodology, which is administrative, that assured people that chain of custody was secure. If you are looking at the modern world where designs are really IP-centric and the IP elements come from all over the world and are touched by thousands and thousands of people, the question is, how do we ensure provenance of these things? So if a chip consists of pre-existing IP and new IP, you can basically think about asking questions like, where did new IP come from? Who designed it? Who touched it? Who edited it? Why did it change? When? And pre-existing IP questions are, what happened to it since it was actually trusted? Because IP is published in source form. It can be edited. Humans cannot find malicious logic in this, or simulation tools cannot find it. And so one of the ideas to consider is that the design tools that want to be compliant to the secure flow basically can be compelled to be extended so that they can authenticate the user before they allow changes to a piece of design. They can calculate the difference between the current and the past version. They can get time, date, map address, IP address, combine all of that into some kind of a key and attach it to a chain of provenance, which can be interrogated at any point in time in the future. So that I'm not saying I'm protecting IP blocks from injection of malicious circuits. I'm simply saying that chain of custody can be managed and observed. And then for the pre-existing IP block is trusted before it's checked into the library, perhaps inside the ARM building, and then it's checked into the library. I think what I'd like to explore is the notion of digital watermarks. So I want the digital watermark computed at that time, but I also want it converted into circuits that are injected back into the design so that the design can always be forced to recompute its watermark at any point in its life, either through simulation, emulation, or live silicon. So you can inject watermarks into unused states and state machines, route them so that they're accessible through JTAG, so that you can always interrogate the provenance of this thing. And so then you can sort of think about expanding this to more complex and larger systems where I would envision that why just think about IP as design elements? Why not embedded software that goes with it? Why not have MCAD tools also establish traceability and so on? So that's kind of, I have one more quick topic, and Andreas touched on this, but this is something of interest to me as well. Distributed systems. I founded and managed Mentor's automotive business unit for 7 years, with flying to Munich every 6 weeks, where my second office was, for 7 years. And I have seen every car company, every airplane company, every helicopter company basically articulate the same requirement to me. We would like to simulate our systems. Not mechanical. We just want to see how the software runs on each node, interacts with the other nodes. When I press the brakes and it involves 3 different subsystems, can I follow the sequence of events? Can I ensure the timing works? So this is a problem that's been articulated. There are some ways the industry is dealing with this. I think there are interesting things to consider here. Can we arrive at the level of abstraction where it is both reasonable in performance, inexpensive to model, and delivers interesting and relevant results? And if you have that, why not optimization? In other words, does this piece of software really have to run on this particular computer? Can it be moved here? And when I did that, did I just accidentally create half a mile of cabling? And if I did, that's not necessarily a good thing. Anyway, that's it. Thank you.
Thank you, sir.
Just like in practice, I was minute and a half over.
That's right. Yeah, consistency is good. Consistently over. No, it's great. A lot of ideas. As you can see, that's what we want out of the new folks. Lots of ideas, lots of opportunities for you to influence their directions, and lots of difficult decisions on our part on figuring out exactly where we're going to head. All right, so now to someone who's been here for a while. One of our elder statesmen is a PM at this point. This will be Paul Tillman, joined from Lockheed, and has really been leading our cognitive EW world, which really straddles that line that I presented earlier. It's probably the prototypical example of straddling that line. It's the RF space being revolutionized by the impact of intelligent decision making and machine learning. So he's going to talk about what's next in that journey.
Thanks, Bill. I want to take a page out of Steve's book and present from pharmacist level here. So, as Bill mentioned, I came prior to DARPA. I was at Lockheed Martin's Advanced Technology Labs, and among other things, we created the first cognitive electronic warfare system. And really what I want to talk about today is what we perceive to be a necessary step if we want to continue to evolve that technology, if we want to continue to evolve the application of AI to the spectrum. And very specifically, I want to talk about a concept that we call digital RF battlespace emulation. And in a nutshell, I want to emulate the real world in RF in real time. And so I'll walk us through some of the computational challenges we see behind doing this. So first, let's start with why. Why is it that I want to emulate what's happening out in the RF world? The real challenge is this, is that spectrum supremacy, spectrum dominance, whatever term you want to use, is really no longer defined by how well a single system works. Having one exquisite radar or having one exquisite jammer no longer really defines whether or not you're going to win or lose that spectrum battle, right? The world is networked. So it's really about how well do all of our radar systems, our EW systems, work at providing SA, situational awareness, to the blue team, while taking that same situational awareness away from the red team. So it's really a problem of scale, right? I want to understand how all of these systems work and interoperate at scale. But my challenge today is that I have a tough choice to make. If I want to understand how a large number of radar and EW systems, let's say communication systems as well, if I want to understand how they interact and work on the battle space, I could make a simulation. I can get excellent scale when I do that, but I compromise on fidelity. I can't simulate the actual waveforms. I don't actually propagate waveforms through space, through an environment. I don't have any of the digital signal processing that resides behind those systems actually present in my simulation. So I'm making a lot of educated guesses. And when you add up too many educated guesses, there's a real question about, did you actually simulate the problem you intended to? On the flip side, we could go do actual open-air tests. We can fly airplanes on ranges with radars and jammers. Excellent fidelity, right? I have all the fidelity of the real world because I'm in the real world, but it's expensive and it's time-consuming. If I have a system and I need hundreds of flights in order to prove out that some new artificial intelligence algorithm applied to a radar or EW system has an improvement, I can't do that through hundreds of open-air flights. It's just too expensive. So hardware-in-the-loop emulation is meant to sort of bridge this gap. A hardware-in-the-loop emulator lets me take real RF systems, connect them to a magical box that takes the signals, propagates them as though they went through a real environment, and spits them out the other side. So you can connect multiple radio systems and make them all appear as though they're moving out in the real world. The challenge is that the hardware emulation systems that we have today do not actually strike a nice balance between simulation and the real world. We get none of the scale, and we don't get close in fidelity. And so what that really means is there's an opportunity here to really advance the state of the art and how we can emulate the real world by doing not just hardware emulation, but massive scale hardware emulation with a real focus on achieving high fidelity. So if we look at the existing world of RF emulation, the commercial systems that we have today are all sort of playing the same game. On the x-axis here is bandwidth, how much of the physical world can we emulate at any point in time. And on the y-axis is the number of ports or devices. How many radio systems can we connect to this? And so we can either have a large number of radio systems, or we can have high bandwidth. And we're trading those off in relative quantities with each other. DARPA's Coliseum from the Spectrum Collaboration Challenge is a really excellent example of, if you want to put a lot of blood, sweat, tears, and time in, what can you get with the state-of-the-art in commercial off-the-shelf electronics? So in the Spectrum Collaboration Challenge, we're asking the basic question, what happens, or what do radio systems look like that are designed to thrive in a world without spectrum management and in a world without the FCC? And doing that, we're expecting our competitors are really combining the worlds of software-defined radio and artificial intelligence. But in order to ask those questions, I need to be able to understand what happens if you take radio systems with no knowledge of each other and, for example, ask them to support first responders responding to a fire and understand what the spectrum looks like when you do that. That meant we needed a system that could allow us to connect 100 radio systems, 100+ radio systems, make them interact in real time in a very repeatable way. With that, we created the Coliseum. Behind the scenes, Coliseum is 64 Vertex 7 FPGAs. And to squeeze every last floating point, or excuse me, every last multiply accumulate out of Coliseum, we actually had to hire one of the people that helped design the DSP logic in the Vertex 7 so that we could get every last bit of compute out of that. But the real challenge is that if we want to advance beyond the communications type emulation that we're doing today to support radar and electronic warfare, we need to be up here. We need to be over 1 gigahertz of bandwidth. We need to have 500+ inputs and outputs. This is a substantial challenge. Why? Well, let's dig into how do you actually emulate the RF world? What is it that we're trying to do? First and foremost, we need to take N systems and make N outputs. N real systems, real radars, real ESM systems on aircraft, real jammers. We need to be able to connect them to some system and have them produce inputs and outputs that everyone can hear. In order to do that, we have to be able to propagate wavefronts. So that radar system, when it's transmitting, it needs to be clear when it's illuminating the upper aircraft and when it's illuminating the lower aircraft. Computationally, this is a problem that grows to this square. So this is challenging. But it's not just about propagating the wavefronts themselves. We're also interacting with other objects in the environment that we don't want. For example, this radar, as it's interrogating that aircraft, is not doing that in free space. It's also interacting with a patch of ground cloth in front of it. So we need to emulate multipath. Again, another problem that grows to the square. But all these radars are out there putting energy into the world. They're creating reflections. So we need to emulate radar cross-sections. And this is actually even more challenging because this problem grows cubically as opposed to the square. So these are the kinds of tasks that we have to emulate. These are the kinds of interactions that our waves have with the real world. We need to do this, but we need to do it in real time. So what does it take? We've studied a handful of potentially exemplary problems. What might we want to do with a system like this? And as a sort of bottom threshold, a floor of what we think it would take, we think that this puts us in the 20 petaflop of compute region, 200+ terabytes per second of interconnect bandwidth, 2 terabits of memory. But perhaps the most challenging part here is the real-time part. You've got to do this in 3 microseconds. So your first reaction might be, Paul, I think you just described a high-performance computer. Why don't we go out and just buy, build, make a high-performance computer? And indeed, if you just focus on the flop count, this would tie for a number 5 or 6 HPC in the world. But the challenge is that I'm not describing a typical high-performance computer. I'm really describing a new class of high-performance computer that is inherently real-time. And so if we take that top-line budget that we just gave you, and we break it down, we have 5 key metrics here. How much compute, memory bandwidth, I/O bandwidth, and crucially, latency. And if we said, we're going to solve that problem with some kind of compute cluster. So let's take it and figure out, on average, what does a processor have to do? Using 156 processors, you get the top-line requirement there. On the spider chart, we've normalized everything. So the blue area, the blue line there, are our requirements normalized to 1. The rest of the colors you see there, we went and plucked processors and FPGAs and GPUs that we find populating our high-performance computers. And every one of them touches 2, maybe 3 of the points that we need, 2 or 3 of the requirements. But no one type of processor actually scratches all of the itches. And so what we really need is we really need to pick a new trade point here. We need a domain-specific architecture that's designed to solve this problem. It's designed not just to have high flop performance, but is also designed to meet real-time latency constraints. So I think we're really at a crossroads right now where it is possible, where it has not been in the past, to do large-scale emulation. But the challenge is that if we think we're going to get there by relying on off-the-shelf existing processing systems, we're sorely mistaken. And so what we really need is we need a new architecture that is optimized to solving this class of problems. A new architecture that's going to give us a high-performance but real-time computer. So with that, thank you.
Nice. That'd be great if you blew an ACL on your way off the stage. All right, so if we could bring the PMs up, and we'll start answering questions. You know, the app, you know, you've been able to load questions throughout the session like we have all week. And we'll answer some of those and then also bring up some of my own. You know, one we heard a lot, right? I think I'll give you my take on where I thought I heard things heading. Serge is really going to pick up the mantle in terms of design from a security perspective, right? Assurance. You know, as I mentioned in the plenary speech, we're at a crossroads from performance has driven the electronics community, security is starting to overwhelm, you know, and we're going to just paralyze ourselves if we can't actually figure out how to balance that. And so just doing things faster is incredibly important for the DoD. One of the reasons we need to get involved in the first place is security. We have national security concerns which are off the beaten path and something that won't be, we can't just trust the commercial domain. And so Serge is going to kind of wind in that direction. Andreas has been leading the charge between chips and ideas and Posh on rapid design, and now how to get those into the field quicker is kind of that next step. Large-scale computing, but applied specifically for that next generation of emulation, is what you heard from Paul. Steve, alternatives computing, right? Getting off that, what do you call it, the sidewalk? The moving sidewalk?
Get off the moving sidewalk.
Right,
it's not
so
going to your gate.
53 years of progress and jumping away and you know, from devices through architectures, and YK looking at that intersection of computation and RF, and so that's an exciting list, but we still got to figure out exactly where we head on all of these. So, all right, I will ask a question that I think is for the office first, which is, you know, we are engaging the commercial sector more broadly, and you know, that's not because we like the commercial sector or don't like the DoD sector. It's just a function of scale. If 8,000 engineering years are being put into an FPGA and a GPU design, we don't have that. I don't have that with my budget. We really don't have it for the broader DoD enterprise, because we have chip designers, but we don't have companies dedicated just solely doing that one thing. So how do you maintain an advantage? And that's, I think, a very, very difficult problem. So I'll give my answer, then open up the floor. You know, the office is trying to form partnerships between the commercial base and the DoD. And it's not that we like either side at all. What we're trying to do is flow from all of the energy that's behind the commercial sector that's thriving within the United States and transition that into the DoD with an opportunity to have those partnerships. So the summit was a good example of trying to get both sides at the table to have the unique DoD needs meet with the commercial capabilities. We aren't going to, you know, we're going to lower the barrier so we can design new stuff ourselves, right? That mixed with customizing or using the commercial capabilities that are emerging from our country is the answer, and it's a mix of both. So, so Andreas, as an example, I know you're working with commercial companies, you work with the EDA vendors as an example. How do you see this world of trying to maintain a asymmetric advantage in an increasingly globalized world?
Well, so in the commercial world, I mean, you see this a lot. You have a free market, but you have tight partnerships, right? And those partnerships are formed over a long time, and you know, you can manage that through just being first there, personal relationships, monetary incentives, exclusivity clauses. So when there's a lot of tools that you can use to create that asymmetrical advantage in the commercial world, and I think there's some opportunity to do similar things in the government side as well.
Yeah. And I think the CHIPS program is a prototypical example, right? By creating an open standard for the country, we're lowering the barrier of where defense, you know, let's say an accelerator or whatnot, can add in a customized block. Easy to say, you still have to do all of it, and I think as Steve has mentioned, right, you can't do 90%. You actually have to be able to program it. You have to actually be able to put that into the field. So it's easy to say we're just going to customize on top of the commercial. The further you put it away from, you know, the rest of the software stack, the more you're going to not be able to actually customize and do things different. Okay, so other questions here. Which was a good one. All right. So we have EDA for photonics waveguides of RF routing. So we don't have that, right? I think that's a good example. So Gordon is somewhere. Gordon is going to take on the optics. So that, you know, as we said, there's overlap between the different sessions. We're definitely looking at doing an optics program. I won't say when, but it's definitely being baked as we speak. And so if we were to do EDA for photonics, it would definitely be in that session. So how about one for Steve? Steve, you hosted a session. We had Carver Mead here. We're blessed to have him be able to kind of help guide us into this next generation of alternative architectures. Can you rehash that? What did you learn, and what was it that you took away from that session?
There were several really important points. One of the major topics we discussed was neuromorphic computing. And yes, DARPA has investigated this in the past. So one reaction would be to say, we tried it. It did not take over the world, so let's let it rest. What I took away from that, though, is DARPA worked on one aspect of that, and then my read was, again, we didn't manage to bite off the whole enough of the problem and solve enough of the pieces to push that to success. But another way to look at that is we have a partial success. We could argue that, well, you know, the digital synchronous CMOS Moore's law juggernaut, we buried that problem under a sea of transistors, and now we can't do that anymore. But I don't think that's fair. I really think the issue is we need to think about the whole problem, and it's that sort of second phase in the technology step. It's the refining the idea to what you really want to do and execute on that. But actually, the big thing that I took out of this, was when when Carver said, no, we latched on one part of this neural model, and we jumped on this network thing, and as an industry, charged ahead saying, we've solved it. And said, there's a lot more under there that we can do. There's a lot more to this model that we haven't even touched yet. And then when Doug chimed in and said, yeah, and now we see this neural network model running out of steam. I said, oh my goodness, it's only been a couple of years. It's already running out of steam. And then I said, no, I'm at DARPA. It's wonderful that it's running out of steam.
That's good. That's good. Yeah, you know, one thing that Doug mentioned was you know, the incumbency issue, right? That suboptimal options exist in the field, you know, for a long time, just because they existed before. And so that resistance to change, and as clouds are built on a certain architecture, you know, just the enormity of actually redoing all of that, right? And what were your thoughts on that? Because I hadn't really thought about the fact that over the last 10 years we've built planetary scale computing in one very particular way. And I know, you know, all my pictures are in one particular version of that. And sucking those down and moving them over, and like I'm just kind of, committed in one direction, right? Personally, right? And we are, as humanity, right, if committed in certain directions. So if you were to invent some radical new architecture, how would you actually handle the incumbency problem?
I leverage it, and so okay, it's there. Actually, I see this as what Doug said, the planetary scale computing. It's this data center moving sidewalk. Mm-hmm. They're building something, and they're going to build the next, and the one after that. And so I see this as a technology direction to be leveraged. So now, how do we leverage that? What is it going to look like? Okay, well, we've got a lot of networking down to localized centers of intense computation. So there's a lot of communication to get to these computation nodes. What does that mean for us? Well, this is an opportunity to construct, as an industry, not necessarily just DARPA, to construct novel computational solutions that can reside inside that environment. Mm-hmm. So where we might not have seen a role of I don't know, quantum computing in my handheld device, maybe I do see a role of quantum computing in this planetary scale computer. It makes kind of sense.
Mm-hmm. Good. Well, one of the things we didn't hear a lot of, which would be, I think, a pretty obvious absence in the slides, is a lot of device work. So maybe to put people's minds at ease, since we have a lot of people that are working on devices out there, talk a little bit about what you're seeing, YK, and kind of how that is shaping your vision for the reservoir computing, or
yeah. So just follow up with Steve and Calvin's session yesterday. So like Calvin say, and the neuromorphic computing, for example, I think there are many different domains or catalogs. And for example, for your eyes neuromorphic function was depending on the sensing and the intensity adjustment. But for your finger, you want to touch, there are different mechanisms of doing that. So to me, I'm a little bit hardware oriented. So I would say will be user or hardware centric application. I think like a DNN, people studied in the 80s, and they post office give a job to Bell Labs to say, hey, if write a zip code with handwrite, then can you use machine to recognize it? That kind of trigger the DNN, and then they use the computation power. Then you can do the street sign recognition and all those things that doing very well with speech, with pattern. But for a lot of other applications like DoD-centric RF and other EM wave and all those optic signature analysis, and they might have different sensors and the user case. Maybe we should develop a separate algorithm rather than the traditional DNN. That's what I'm kind of interested in exploring, like reservoir computing with time delay element. So you can have a short-term, long-term time delay with kind of folded processing element. Is more compact and hopefully will be lower latency. But definitely there are other issues like stability in this feedback system, and how can you avoid a chaotic situation to make an intelligent decision. So that's kind of important. Yeah.
All right, well, we're actually over time, and apologize because there's probably a lot more we could get to, but they're all here. They're open for business, so feel free to give them your ideas, and that's what we're here for. So we're here to listen, and you will be seeing hopefully a flurry of activity in the fall as we do this sort of next round of electronics investment. So thank you.